We worked out an amplitude of probability for the field to go from vacuum to vacuum over an infinite time using many path formulation. We determine a Lagrangian for scalar fields, which has a free part and a part containing interaction within the field. So for instance, when a disturbance of the field propagates and hit another disturbance of the field, remember that we call that particles, we could have an inelastic collision, we could have creation of new disturbance of the field, we could have annihilation, etc. So that part is contained in the interaction, and we will see that in more details later, in particular when we will introduce Feynman diagrams. In general, it is impossible to solve our amplitude with such a Lagrangian. So we need approximation. The first approximation which comes into mind is to take the classical limit. And we have the classical limit when the action is much larger than h bar. In that case, we get the Euler-Lagrange equation. So we just have to plug in the Lagrangian into the Euler-Lagrange equation in order to get classical equation of motion for our field. That's generally called classical field theory. Returning to the quantum case, we saw that we can solve this path integral in the case of free field, so when we turned off all the interaction terms. In that case, the path integral is simply expressed as a Gaussian path integral, which can be solved exactly. And we saw that in that case, the effect of the source is only to change the phase of the path integral. And what we got was a phase which could be expressed as function of two integrals for the source and also a propagator. So what we have here is a source creates a disturbance of the field, propagates from x to y, and then is annihilated later on in y. We then got an expression for the free propagator, and we found that for disturbance to propagate efficiently, this propagator must be large, and that's obtained when we have k squared is equal to m squared. So if we have a source and a sink, the disturbance will only propagate when k squared is equal to m squared, which means that we have a disturbance on mass shell, because in that case we have e squared equal p squared plus m squared. And that's what we call a particle. So a particle is a disturbance of the field which propagates on mass shell. We then used a different setup with our sources in order to study interaction between sources, so not to be mistaken with interaction within the field. Here we only looked at the change of energy induced by the action of sources on the field. So we have two sources at some distance r pressing on the field, and that change in energy, and the change in energy is a Yukawa potential. And it's attractive because we gain energy when the two sources get closer to each other. And in that case, the disturbance of the field is not on mass shell, clearly. So we sometimes say that the interaction between the sources is mediated by virtual particles. Remember that virtual particles is only disturbance of the field which are out of mass shell. This interaction is typically of a range of the inverse of the mass, and remember that the mass appears as a quadratic potential in the Lagrangian. And this is the same mass which appears as disturbance of the field propagating on mass shell, so that the mass of particles. Therefore, when we have an interaction, we must have field mediating this interaction, and if we have a field, we must have a particle corresponding to excitations on mass shell of this field. So that's how sometimes we discover new particles, and that was the case for the pion as one of the mediators of the interaction between nucleons. Interestingly, if you take this mass to be zero, you end up with what we call an infinite range interaction. And in particularly, that corresponds to a potential energy which is in 1 over r, like electromagnetism and gravity. Therefore, the photon, which is a mediator of the electromagnetic interaction, and the graviton, which is, if it exists, the mediator of gravitation, have to be massless particles because their corresponding potentials are in 1 over r.